Reality itself might be hiding fundamental flaws. Across the cosmos, astronomers and physicists are uncovering strange glitches in the fabric of space-time, cosmic errors that defy every law of physics we think we know. By the end of this journey, you will discover 25 of the universe's most baffling secrets, from spacecraft that mysteriously slow down to stars that vanish without explanation. We will explore signals from the void that hint at intelligence and forces that pull entire galaxies toward an unseen horror. What single cosmic anomaly makes you question everything you thought was true? Our journey into the cosmic unknown begins close to home, with two robotic pioneers sent to explore the outer planets. After completing their missions, Pioneer 10 and Pioneer 11 continued their silent journey into the abyss. But something was wrong. Back on Earth, scientists meticulously tracking their trajectories noticed a tiny, persistent drift. The spacecraft was slowing down as if an invisible hand was gently applying the brakes. This minuscule deceleration was barely perceptible, less than a billionth of the gravity we feel on Earth, but it was undeniably real and completely unexpected. It defied every calculation based on the known gravitational pull of the Sun and planets. For decades, this pioneer anomaly remained a profound mystery. Some theorized it was the faint, gentle push of heat radiating from the spacecraft's own power systems, a thermal whisper nudging them off course. Others wondered if we were seeing the first hints of a deeper truth, a flaw in our understanding of gravity itself, requiring a modification to Einstein's laws on cosmic scales. It was a ghost in the machine, a subtle reminder that even in the vacuum of space, the universe holds onto its secrets tightly. This same ghostly tug is not alone. Years after the Pioneer mystery emerged, a similar enigma appeared much closer to Earth during what should have been routine cosmic maneuvers. Spacecraft performing gravity assists, using our planet's pull like a slingshot to gain speed, were experiencing something impossible. Probes like Galileo and Rosetta, on their way to explore Jupiter and a comet, swung around Earth in a perfectly calculated dance. Yet, as they flew away, radio tracking revealed a tiny, unaccountable boost in their velocity. It was as if an unseen hand had given them an extra, gentle push. This is the flyby anomaly. The speed increase was minuscule, often just a few millimeters per second, but in the precise world of orbital mechanics, where trajectories are calculated to perfection, it was a glaring error. For scientists, it was like watching a perfectly thrown boomerang return just a little faster than it should every single time. The question became immediate and profound. Were our measurements flawed, perhaps due to the subtle drift of continents or the uneven distribution of Earth's mass affecting its gravity field? Or were we witnessing a crack in the foundation of physics itself, a hint that our understanding of gravity and motion is incomplete on a planetary scale? The debate continues, a quiet hum of uncertainty beneath the roar of every rocket launch, reminding us that even the most trusted paths through our own cosmic backyard can still hold surprising secrets. But these strange tugs on our spacecraft are just whispers compared to the cosmic roar of entire galaxies in motion. Far beyond our local group, astronomers have detected a phenomenon so vast it defies the very expansion of the universe itself. They call it the dark flow. Like leaves caught in a river current, entire clusters of galaxies are drifting in a specific, coordinated direction, moving at incredible speeds that dark energy alone cannot explain. It is as if something immense, lying far beyond the edge of the observable universe, is pulling on the cosmic fabric. This is not a local drift, it is a current flowing through the cosmos on a scale we can barely comprehend, suggesting that our universe might be just one part of a much larger and utterly unknown structure. This mysterious pull finds a focal point closer to home in one of the most terrifying gravitational anomalies ever discovered, the Great Attractor. Located in the direction of the Centaurus constellation, This region of intergalactic space exerts a colossal gravitational force, pulling our own Milky Way and millions of other galaxies toward it at a staggering 2 million kilometers per hour. For decades, its true nature was hidden from our view, shrouded by the dense plane of our own galaxy, a zone of cosmic avoidance filled with gas and dust. What could possess such power? The answer is both humbling and awe-inspiring. The Great Attractor is not a single, monstrous object, but a gravitational focal point, the heart of the Laniakea supercluster, our home supercluster of over 100,000 galaxies. Visualize our universe not as a static expanse, but as a web of flowing rivers, with galaxies streaming along vast filaments toward these dense gravitational basins. We are part of that flow, caught in a silent, unstoppable current toward a center of mass we once could not see. The question now is what other invisible currents are pulling at the cosmos, guiding its ultimate destiny from the shadows. Yet, even as entire galaxies drift in these vast currents, the universe holds deeper, more intimate mysteries on the smallest of scales. The rules governing the very small are not the solid laws we know, but a realm of probability and paradox where particles can be in two places at once. This begins with what Einstein called spooky action at a distance, known today as quantum entanglement. Imagine two particles born together, then flung to opposite ends of the galaxy. If you measure one and find it spinning clockwise, its twin instantly spins counterclockwise, no matter the distance between them. They communicate faster than light, a connection that seems to defy the cosmic speed limit, as if the space between them does not exist at all. It is a profound glitch in logic, suggesting that at its core, the universe is fundamentally interconnected in ways we cannot yet fathom. This strange behavior extends to how particles move. In our world, you cannot walk through a wall, but in the quantum realm, particles perform this magic routinely through a process called quantum tunneling. An electron faced with an impenetrable energy barrier does not need to go over it. There is a small, calculable probability that it will simply appear on the other side as if it teleported. This is not just a theoretical idea, it is the principle that makes the sun shine, allowing protons to overcome their mutual repulsion and fuse together, creating the starlight that fuels the cosmos. But the strangest quantum anomaly of all reveals that reality itself may be undefined until we look at it. This is the lesson of the double-slit experiment. When you fire tiny particles like electrons at a barrier with two slits, they do not behave as solid little balls. If no one is watching, they act like waves, passing through both slits at once and creating an interference pattern on the other side. Yet, the moment you place a detector to see which slit an electron goes through, it abruptly changes its behavior, acting like a single particle, and the wave pattern vanishes. The very act of observation, of measurement, seems to collapse the wave of possibilities into a single, solid fact. It forces us to ask a deeply unsettling question. Does the universe exist in a definite state when we are not looking, or is it a shimmering cloud of potential waiting for a conscious mind to bring it into focus? This unsettling idea that observation defines reality finds a cosmic echo in the oldest light we can see. The afterglow of the Big Bang, the cosmic microwave background, blankets the entire sky, a fossilized snapshot of the infant universe. For decades, this radiation was considered the ultimate proof of a uniform cosmos, a nearly perfect sea of microwaves demonstrating that the universe has no preferred direction, no center, and no edge. This is the cosmological principle, the bedrock of modern cosmology. But then we looked closer. When scientists created a detailed map of this ancient light, they found something that should not be there. Subtle temperature variations in the radiation appeared to align along a specific axis, a mysterious corridor in the sky that some have boldly nicknamed the axis of evil. This is not a malevolent force, but a label for a finding so unsettling it seems to undermine the very foundation of our cosmic worldview. The universe, it appears, might have a preferred direction after all, a spine running through the cosmos that challenges the idea of perfect uniformity. How could this be? If the Big Bang was a perfectly symmetric event and inflation stretched the universe into smooth homogeneity, why would this ancient light bear the mark of a direction, a cosmic alignment that should have been erased in the first moments of time? The implications are staggering. It could mean our understanding of the Big Bang is fundamentally incomplete, or that inflation, the theory of the universe's rapid expansion, happened in a lopsided way. Perhaps we are seeing the gravitational imprint of something from before the Big Bang, or evidence that our universe is just one bubble in a vast multiverse brushing against another. The axis of evil is a quiet, statistical whisper in the data, but its message is deafening. It suggests the cosmos may not be the random, isotropic expanse we believed it to be, but a place with a hidden structure, a secret architecture written into the first light of creation. While the cosmos whispers its secrets through ancient light and quantum riddles, it once seemed to shout. On a quiet Ohio night in August 1977, a radio telescope known as the Big Ear was engaged in its routine scan of the heavens. It was listening for nothing in particular and for everything imaginable. Suddenly, the silence was shattered. For 72 breathtaking seconds, a signal blasted through the void, so powerful and so perfect it defied all natural explanation. It came from the direction of the constellation Sagittarius, and it pulsed on the exact frequency of 1.42 GHz. This is the sacred channel of the universe, the emission line of neutral hydrogen, the most common element in space. It is the frequency scientists had long predicted an intelligent civilization would use to broadcast its existence, because it is the natural radio station of the cosmos, a channel any advanced species would know to tune into. The signal was 30 times stronger than the background noise, a clear, artificial sounding tone that rose to a peak and then faded away, exactly as you would expect from a beacon passing through the telescope's fixed field of view. When astronomer Jerry Amon reviewed the computer printout the next day, he circled the alphanumeric sequence representing the signal's incredible intensity and, in a moment of pure astonishment, scribbled one word in the margin. Wow! The wow signal was everything they had been waiting for, a perfect candidate for a message from the stars, yet it was a message that was never repeated. Despite decades of searching pointing the most powerful radio dishes toward that same patch of sky, the silence has remained unbroken. So what was it? The signal was so brief and localized it could not have been a reflection from a passing satellite or a piece of space debris. Some have proposed a comet, but the frequencies do not match, and no known comet was in that position at that time. It was a one-in-a-million event, a cosmic flash in the pan that has fueled both scientific curiosity and profound wonder ever since. Was it a momentary glitch in our own technology, a burst of natural astrophysics we do not yet understand, or was it a fleeting hello from a distant civilization, a message sent across the light years that we heard for just 72 seconds before the universe once again went quiet? That profound silence from the stars is matched only by the silence of the cosmos itself, a void filled with something we cannot see. While the wow signal remains a fleeting mystery, our universe is dominated by a far more persistent and pervasive enigma, dark matter. We know it exists because of its immense gravitational pull, holding galaxies and galaxy clusters together. But when we look closer at how this invisible substance should behave, our simulations of the cosmos clash with stark reality. These are not minor disagreements, they are fundamental flaws in our understanding of how the universe is structured. The first of these puzzles is called the missing satellite problem. Our most sophisticated computer models, which simulate the evolution of the universe from the Big Bang to the present day, show a very specific picture. They predict that large galaxies like our own Milky Way should be surrounded by a swarm of hundreds, even thousands of smaller dark matter clumps. each of these clumps should have enough gravity to pull in gas and form a small, visible dwarf galaxy. Yet when we look out into the sky, we find only a few dozen. The question is simple and baffling. Where are all the missing galaxies? It is as if we built a perfect model of a solar system, complete with all the planets, only to look through a telescope and find half of them are simply not there. This discrepancy suggests that something is wrong, either with our models of how dark matter behaves or with our understanding of how stars form in these tiny, fragile environments. Perhaps the conditions in these small clumps prevent galaxies from lighting up, leaving them dark and invisible. Or maybe our concept of dark matter itself needs a radical revision. This missing satellite problem points to a cosmos that is far quieter and far emptier than our theories insist it should be, but the strangeness does not stop there. An even deeper conflict lies at the very heart of galaxies, known as the core cusp problem. According to our standard models, dark matter should be densely packed at the center of galaxies. The density should spike sharply, creating a pronounced cusp like a steep mountain peak. However, observations of the motions of stars and gas within dwarf galaxies tell a very different story. Instead of a steep cusp, the dark matter appears to be distributed in a much gentler way, forming a wide, flat core. Imagine stirring a cup of coffee with thick syrup at the bottom. You would expect the syrup to remain concentrated in the center, but instead you find it has spread evenly throughout the entire cup. This is the essence of the core cusp problem. The dark matter is not behaving as a simple, cold, and collisionless substance should. Something is preventing it from clumping at the centers of galaxies as predicted. This could mean that dark matter particles have properties we have not anticipated. Perhaps they can interact with each other in subtle ways, or even with normal matter, smoothing out those dense central peaks over time. These two problems, the missing satellites and the strange cores, are not just small errors in our cosmic calculations. They are glaring red flags, indicating that the dominant ingredient of our universe, the very scaffolding upon which galaxies are built, is far more complex and mysterious than we ever imagined. The silent architecture of dark matter is not the only cosmic structure hiding in plain sight. From the deepest voids between galaxies come sudden, violent explosions of energy that outshine entire galaxies in the blink of an eye. These are fast radio bursts, or FRB. For a few fleeting milliseconds, a single burst can release more energy than our Sun will emit over 80 years. Their sources are billions of light-years away, cosmic flashbulbs so powerful we can detect them across almost the entire universe. The first was discovered in 2007, hidden in archival data from a radio telescope in Australia, and since then hundreds more have been detected. Each one is a cataclysm, a brief, brilliant scream in the radio spectrum. For years, every single one was a one-off event, a sudden, inexplicable detonation with no repeat performance. This pointed toward a catastrophic source, a single, universe-altering event that destroyed its own engine. Theories flourished, suggesting the collisions of ultra-dense neutron stars, the violent death throes of massive stars collapsing into black holes, or the shattering of asteroids onto the surfaces of distant, magnetized dead stars called magnetars. Each theory painted a picture of ultimate, final destruction. Then everything changed. In 2016, astronomers found one that did the impossible. A source, now known as FRB 121102, began to repeat. It was not a single, catastrophic death, but a persistent, periodic voice. This was a fundamental shock to the system. How could a cataclysmic event happen over and over again? The repeating bursts ruled out any model that involved the total destruction of the source. Suddenly, the most dramatic explanations fell away and a new, deeper mystery took their place. The most dramatic recorded burst came from a galaxy over 3 billion light-years away, a single pulse so intense it was named the Lorimer burst after its discoverer. To visualize its power, imagine concentrating the entire energy output of hundreds of millions of stars and releasing it all in the time it takes a camera flash to go off. This is not a slow building fire, it is a cosmic gunshot. The existence of both one-off and repeating FRBs suggests we are dealing with at least two different types of phenomena, perhaps multiple cosmic beasts capable of such staggering displays. The repeating signals, in particular, point to an object that can survive its own ferocious outburst, something like a hyper-magnetized neutron star precessing like a wobbly top, or a black hole interacting with a dense companion star, periodically devouring pieces of it and screaming in radio waves with every bite. These brilliant, transient events are cosmic telegrams, carrying encoded information about the distant, invisible matter they pass through on their long journey to us. Each one is a brief, fiery crack in the silent night, a reminder that the universe is far from quiet and that its most powerful voices often speak only once. These brilliant radio flashes exist for mere instants, yet they force us to question the very nature of time itself. Time, the steady rhythm of our universe, might not be as reliable as we believe. High above our planet, on board the International Space Station, a silent experiment runs continuously. Ultra-precise atomic clocks, the most accurate timekeepers ever built, tick away the seconds. Yet, when compared to their identical counterparts on Earth, they consistently run just a little bit faster. This is not a mechanical error, it is a direct confirmation of Einstein's theory of relativity. Time itself flows faster where gravity is weaker. For the astronauts in orbit further from Earth's gravitational pull, time literally accelerates, if only by microseconds each day. This is gravitational time dilation in action, a proven fact that feels like pure science fiction. But what happens when we push these principles to their absolute limits? Experiments testing the foundations of special relativity have returned with unexpected, subtle wrinkles. When scientists measure the decay rates of unstable particles accelerated to near light speed, the slowing of their internal clocks matches predictions. Yet, in the bizarre world of quantum mechanics, some observations do not align perfectly. There are hints buried in the data that certain particles might experience time in a slightly different way, as if the fabric of space-time has a tiny, inherent graininess we cannot yet see. This leads to the most profound temporal puzzle of all, one that strikes at the heart of cause and effect. In our everyday world, you must flip a light switch before the bulb illuminates. Cause always comes before effect. This is the unbreakable arrow of time. But in certain quantum experiments, this logic collapses. Scientists can create setups where two particles become entangled, their fates linked. In these experiments, measuring one particle seems to instantly influence the state of its partner. But the order of those measurements can be arranged so that, from different perspectives, the effect could be argued to happen before the cause. It is as if time is looking at itself in a funhouse mirror, where the sequence of events becomes blurry and undefined. This does not mean we can build a time machine, but it strongly suggests that at the most fundamental level, the universe does not rigidly enforce a single timeline. The past, present, and future might be more fluid concepts than we ever dared to imagine, woven together in a quantum tapestry where the arrow of time is not a law, but perhaps just a prevailing habit. Far from the quantum realm's fluid time, a star over 1,000 light-years away began to act strangely, its light telling a story no one could decipher. Astronomers call it KIC 8462852, but you likely know it as Tabby's star. It was discovered not by a seasoned astronomer, but by citizen scientists, volunteers sifting through public data from NASA's Kepler telescope, who noticed its light was doing something impossible. Stars can dim slightly when planets pass in front of them, creating a clean, predictable, and repeating pattern. But Tabby's star was different. Its light would dip by tiny amounts, then plummet by over 20% in chaotic, asymmetrical plunges that lasted for days or weeks. This was not the signature of a simple spherical planet. It looked more like a vast, tangled swarm of something was orbiting the star, blocking its light in a jagged, unpredictable rhythm. The most dramatic event was a dimming of 22%, a staggering amount that would require an object far larger than the star itself to cause. The scientific community was electrified. What could possibly block so much starlight? The most tantalizing and controversial hypothesis was that of an alien megastructure. Imagine a civilization so advanced it has begun to construct a Dyson sphere, a colossal swarm of energy-collecting panels encircling its sun. Such a structure, incomplete and irregular, would create exactly the kind of bizarre, non-repeating light curves we observed. It was a breathtaking idea, a potential signal of intelligence on an almost unimaginable scale. Yet, science demands natural explanations first. Astronomers scrambled to find one. Could it be a vast cloud of comets shattered by the star's gravity into a swirling debris field? Or perhaps a family of giant, dusty planets with enormous, clumpy rings? Maybe the star itself was recovering from a planetary collision, surrounded by the glowing, cooling debris of a shattered world. Each idea was explored, and each one fell short. A giant comet swarm could explain some dips, but not the long-term, century-long dimming also observed in historical data. Dusty planets could not account for the sheer depth and aperiodic nature of the dimming. No single, conventional model could fully explain the complete, bizarre light signature of Tabby's star. It remains an enigma, a celestial beacon whose message we have not yet decoded. It is a powerful lesson in cosmic humility, showing us that even when we rule out the impossible, the universe can still leave us with the extraordinary. While Tabby's star presents a modern riddle, a far more ancient and fundamental discrepancy lies in the very elements forged at the dawn of time. In the first few minutes after the Big Bang, the universe was a seething nuclear furnace. During this brief, explosive period known as Big Bang nucleosynthesis, the primordial protons and neutrons fused to create the universe's first atomic nuclei. The models predicting this process are stunningly accurate for the two lightest elements, hydrogen and helium. The amount of helium we observe in the oldest stars matches the theoretical predictions with incredible precision, a triumph for cosmology. But for the third lightest element, lithium, the math falls completely apart. Our best models of the infant universe insist there should be about 3 times more lithium in the oldest stars than what we actually see when we point our telescopes at them. This is the cosmological lithium problem, and it is not a small oversight. It is a fundamental flaw in our story of creation. How could our calculations be so perfect for hydrogen and helium, yet be so dramatically wrong for lithium? This is not about later processes in stars. This is about the pristine, initial ingredient list of the cosmos itself. The oldest stars act as cosmic time capsules, preserving the chemical makeup of the early universe, and they all tell the same story: lithium is missing. It is as if a master chef followed a perfect recipe, but when you taste the dish, one key spice is only a third as strong as it should be. This forces us to question what we thought we knew about those first fiery minutes. Perhaps unknown particles were present, influencing the nuclear reactions. Maybe the density of the universe was slightly different, or the nuclear reaction rates themselves need revision. This missing lithium is a quiet but persistent ghost from the birth of everything, a clue that our understanding of the universe's very first moments remains tantalizingly incomplete. The silent ghost of missing lithium is a puzzle from the universe's first moments, but a far more dramatic rebellion was discovered much closer to home, in the very motion of the galaxies around us. For centuries, we believed we understood the gravitational dance of stars. Just as planets closer to the Sun orbit faster than those farther out, stars at the edge of a galaxy should orbit more slowly than those near its bright center. This was the unshakable prediction of Newtonian gravity, a rule that seemed as solid as any in physics. But in the 1970s, astronomer Vera Rubin and her colleague Kent Ford turned this rule on its head. They meticulously measured the rotation speeds of stars in the Andromeda galaxy, expecting to see those on the outskirts lagging behind. To their astonishment, they found the opposite. Stars at the very edge of the galaxy were orbiting just as fast as those near the center. It was as if the entire spiral disk was spinning like a rigid record, a solid plate, rather than a swirling fluid where the outer parts naturally slow down. This was the galactic rotation curve anomaly, and it was a direct, undeniable violation of the predicted gravitational law. The only possible explanation was that there was more to the galaxy than meets the eye. A vast, invisible sphere of something was enveloping the visible disk, providing extra gravitational glue to whip the outer stars to such incredible speeds. This something could not be seen. It did not emit or absorb light, but its gravitational pull was undeniable. It was the first robust, observational evidence for what we now call dark matter. Vera Rubin's work transformed a theoretical curiosity into a central pillar of modern cosmology. Yet, decades later, this foundational anomaly continues to challenge us in new ways. As our telescopes have grown more powerful, we have observed the same flat rotation curves in dwarf galaxies, where the dark matter should dominate completely. But here, the predictions of the standard dark matter model and the observations often clash, creating tensions that echo the core cusp problem. Some of these tiny galaxies spin slower than expected, others faster. It is as if dark matter behaves slightly differently in different galactic environments, refusing to conform to a single, simple set of rules. This has led a small but persistent group of physicists to propose a radical alternative, that our theory of gravity itself is wrong on galactic scales. This idea, known as modified Newtonian dynamics or MUND, suggests that gravity strengthens slightly where its pull becomes incredibly weak, eliminating the need for dark matter entirely. While MUND can explain the flat rotation curves surprisingly well, it struggles to account for all the gravitational evidence we see, such as the bending of light in giant galaxy clusters. So the mystery that Vera Rubin uncovered remains wide open. Is the universe filled with a mysterious, invisible substance that shapes the cosmos, or are we witnessing the slow breakdown of gravity, a force we thought we understood? The silent spin of every galaxy holds the answer, a secret it has yet to fully reveal. The silent spin of galaxies hints at forces we cannot see, but in a laboratory on Earth, an engine was built that seemed to defy a fundamental law of motion. This is the story of the M drive, a device that looked like a simple, sealed metal cone, but promised to rewrite the rules of spaceflight. According to Newton's third law, for every action, there is an equal and opposite reaction. A rocket must expel propellant out its nozzle to push itself forward. The M drive, however, claimed to create thrust from nothing. By bouncing microwaves around inside its sealed copper cavity, it appeared to push against the very fabric of space-time itself, producing a tiny but measurable force without any exhaust. The first results, emerging from a small team in the United Kingdom, were met with immediate and profound skepticism. How could you push against the universe without throwing something away? It was like trying to move a car forward by sitting inside and pushing on the windshield. The reported thrust was minuscule, just a few thousandths of a Newton, but if it were real, the implications were staggering. A spacecraft equipped with such an engine could, in theory, accelerate continuously for months or years, reaching the outer planets in weeks and the nearest stars within a human lifetime, all without needing to carry a single drop of fuel. The dream of a true starship seemed to flicker to life in a most unexpected way. This promise fueled a decade of intense global investigation. Research groups at NASA Eagleworks Laboratory in Germany and in China all built their own versions of the M drive. To the astonishment of many, several of these independent teams reported detecting a small, persistent thrust, just as the original inventors had. the scientific community was thrown into a fierce debate. Was this the dawn of a new physics, a loophole in the conservation of momentum, or were they all being fooled by a subtle, insidious experimental error? The critics were relentless. They proposed a host of alternative explanations. Perhaps the thrust was caused by the device heating the air around it, creating tiny thermal currents that pushed on the test apparatus. Maybe the electrical currents powering the microwave generator were creating magnetic interactions with the Earth's own magnetic field. Or it could have been an artifact of the sensitive measuring equipment itself, which used a torsion balance to detect the slightest push, a system vulnerable to vibrations and thermal expansion. Each new paper was a volley in a scientific war, with one side claiming a genuine anomaly and the other dismantling the claim with a new potential source of error. The controversy reached its peak when a group in Germany built an incredibly precise experiment in a near-perfect vacuum. They, too, detected thrust, but they also found something deeply revealing. When they rotated the entire apparatus, changing its orientation, the direction of the thrust changed with it. This was a telltale sign of an interaction with a magnetic field or another local environmental factor, not a true propellantless drive pushing against the quantum vacuum. The dream began to fade. The scientific consensus today leans heavily toward the M drive being a fascinating lesson in experimental pitfalls, a phantom thrust born from forces we understand all too well. Yet its legacy endures. It forced physicists to re-examine the deepest principles of their field and inspired a new generation to question the impossible. The M drive may not have given us the stars, but it gave us a powerful reminder that even our failures can push the boundaries of discovery. While the M drive taught us to question our own experiments, the universe itself sometimes fires bullets so powerful they should not exist. These are cosmic rays, atomic nuclei traveling through space at nearly the speed of light. Most are low energy, a constant drizzle from our own galaxy. But a few are different, carrying so much energy they defy all known limits. In October 1991, an observatory in Utah detected a single particle that sent shockwaves through the world of physics. It was a proton, a tiny subatomic speck, but it was moving with the kinetic energy of a well-thrown baseball, all compressed into a single, invisible bullet. They called it the "Oh my God" particle. Its energy was so immense, roughly 50 million times greater than what we can produce in our most powerful particle collider, that it seemed to break the laws of physics. According to our best theories, such a particle should not be able to travel very far through the cosmos. The universe is filled with the faint glow of the cosmic microwave background, the leftover heat from the Big Bang. For an ultra-high energy proton, this background radiation is not a gentle warmth, it is a thick fog. The proton should constantly collide with these microwave photons, losing energy with every impact until it slows to a crawl over a relatively short cosmic distance. The "Oh my God" particle, and others like it, should not have been able to reach Earth from any source more than 150 million light-years away. Yet, when astronomers traced its path backward, they found no likely source within that local volume of space. It came from the great emptiness between galaxies, a void with no known object capable of such an unimaginable feat of acceleration. This is the cosmic ray anomaly. What natural particle accelerator could possibly exist out there, capable of hurling a single proton with the force of a major league fastball? Our best candidates are the most violent events in the universe, the cataclysmic deaths of massive stars in supernova, or the ferocious jets erupting from supermassive black holes at the centers of active galaxies. But even these cosmic powerhouses seem barely capable of reaching the energy levels we have recorded. It is like discovering a single grain of sand on a beach that was launched by a volcanic eruption from another continent, a feat that defies every known law of ballistics. The mystery deepens because these ultra-high energy cosmic rays do not arrive from random directions. They appear to cluster, hinting at specific, hidden sources in the distant cosmos, yet we cannot identify the engines that create them. Their existence forces us to consider truly exotic possibilities. Could they be the decay products of super-heavy theoretical particles left over from the Big Bang? Or are they the signature of defects in the very fabric of spacetime itself, cosmic strings snapping and releasing unimaginable bursts of energy? Each one of these rare particles is a messenger from the deepest voids, carrying a simple, terrifying message that our understanding of the universe's most powerful forces is still in its infancy. The universe is expanding, but we cannot agree on how fast. This is not a small disagreement among scientists. It is a full-blown crisis in cosmology known as the Hubble Tension. On one side, we have the ancient light of the cosmos, the cosmic microwave background, a pristine snapshot of the infant universe from over 13 billion years ago. By meticulously mapping its subtle fluctuations, the Planck satellite and other missions have given us a highly precise prediction for how fast the universe should be expanding today, a value known as the Hubble constant. This is the view from the beginning, a cosmic starting gun whose echo tells us the current pace. On the other side, we have the local universe, our own cosmic neighborhood. Here, astronomers use celestial lighthouses called Cepheid variable stars and cataclysmic supernova explosions. These are standard candles, objects with a known intrinsic brightness. By measuring how much dimmer they appear to us, we can calculate their distance with remarkable accuracy. When you combine this distance with measurements of how fast these objects are moving away from us, you get a direct modern measurement of the Hubble constant. The problem is stark and undeniable. The two numbers do not match. The local measurements using stars and supernova consistently show a universe that is expanding significantly faster than the ancient light from the cosmic microwave background predicts. This is not a minor statistical fluke. The gap is now so large that the chance of it being a simple error is less than 1 in a million. It is as if you carefully calculated the entire life of a tree from the rings in its trunk, predicting its exact height today, only to go outside with a tape measure and find the tree is several feet taller than it should be. The foundation of our cosmic timeline is cracking. What could be causing this fundamental discrepancy? Perhaps there is something we do not understand about the standard candles themselves. Could Cepheid variables be subtly different than we think, throwing off our distance measurements? Teams have checked and rechecked, using new data from the Hubble Space Telescope and now the James Webb Space Telescope, and the tension only grows stronger. This leads to a far more thrilling possibility that our standard model of cosmology is incomplete. Maybe dark energy, the mysterious force driving the acceleration, is not constant but has been changing over time, growing stronger and pushing the universe apart faster than anticipated. Or perhaps a new, unknown type of subatomic particle was present in the early universe, a relic that subtly altered the physics of the Big Bang's afterglow. Some have even speculated about exotic ideas, like our galaxy sitting in a vast cosmic void where the density of matter is lower than average, creating a local distortion in the expansion rate. Each potential solution points toward new physics, a discovery that would force us to rewrite the textbooks. The Hubble tension is more than just a number. It is a direct challenge to our story of the cosmos, a signal that the universe still holds profound secrets about its own birth, life, and ultimate fate. This deep conflict over the expansion rate forces us to confront an even more fundamental schism at the heart of physics itself. For over a century, we have lived with two separate rule books for the universe. One governs the immense cosmic scale of galaxies and black holes, a theory of graceful geometric curves known as general relativity. The other rules the bizarre, probabilistic world of atoms and particles, a theory of chance and connection called quantum mechanics. Both are spectacularly successful in their own domains, yet they are utterly incompatible. They speak different mathematical languages and describe reality in mutually exclusive ways. This is the great unsolved problem of quantum gravity. To understand why uniting them is so difficult, picture a perfectly smooth, frozen lake. This is Einstein's space-time, a continuous fabric that bends and warps under the weight of stars and planets. Now picture that same lake not as solid ice, but as a seething, bubbling foam, where trillions of tiny bubbles constantly pop in and out of existence. This is the quantum world where nothing is ever still or perfectly defined. The challenge of quantum gravity is to somehow merge the smooth, frozen lake with the chaotic, bubbling foam. The conflict becomes starkly clear when we look at a black hole. According to general relativity, a black hole is simplicity itself. Its entire identity is defined by just three things: its mass, its spin, and its electric charge. If you throw a grand piano, a library of books, or a complex living creature into a black hole, the theory insists that all that intricate information is utterly and permanently destroyed, erased past the event horizon. But quantum mechanics has a fundamental, unbreakable rule: information can never be truly lost. It may be scrambled beyond recognition, but it must, in principle, be recoverable. This is the black hole information paradox. If a black hole evaporates over eons via Hawking radiation, what happens to the information locked inside? Does it leak out in the radiation, violating relativity's core tenets? Or is it lost forever, violating quantum law? We are left with a profound contradiction, a cosmic error message that tells us our understanding of reality is broken at the most fundamental level. The difficulty is more than just theoretical, it is profoundly practical. General relativity tells us that any accelerating mass should create ripples in space-time, gravitational waves. We have magnificently detected these waves from colossal events, like the mergers of black holes. But what about the quantum realm? Every single particle, every electron and quark is constantly jittering and accelerating. According to the rules, each one should be emitting its own tiny, infinitesimal gravitational wave. Yet we have no theory, no conceivable experiment that could ever detect such a whisper. The signal is drowned out by the quantum noise of the universe itself. We are trying to hear the gentle pluck of a single string, but the entire symphony is playing at once. This is the core of the challenge. Our two most powerful theories cannot even agree on what reality is made of at its smallest scale, leaving us with a universe that is beautifully described by two sets of rules, and a deep, lingering suspicion that both are just shadows of a far grander truth we have yet to perceive. These two cosmic anomalies are pure mathematical prophecy, born directly from the equations of general relativity. If a black hole is a one-way door into a gravitational prison from which nothing can escape, then a white hole would be its perfect opposite. Picture a black hole running backward in time, an exit-only gateway through which matter and energy violently erupt into the universe. It would be a cosmic fountain of infinite pressure, a source of relentless light and radiation that could never be entered, only fled from. While black holes are proven cosmic realities, white holes remain entirely theoretical, a beautiful symmetry in the math with no observational evidence to support their existence. Some have speculated that the Big Bang itself could be viewed as a primordial white hole, a singular event of creation. Others wonder if the mysterious, unimaginably powerful gamma-ray bursts we detect could be the final, explosive death throes of a white hole. So far, no such cataclysm has matched the predicted profile. The universe seems to have a strong preference for one direction, an arrow of time that favors the pull of black holes over the push of their hypothetical twins. Yet, if we thread the needle between these two theoretical extremes, we arrive at an even more fantastic possibility. What if a black hole and a white hole were connected? This is the concept of the Einstein-Rosen bridge, more popularly known as a wormhole. A wormhole is a shortcut, a theoretical tunnel through the folded fabric of space-time. Imagine the universe is a vast sheet of paper. To get from one end to the other, you would have to travel the entire length. But if you could bend the paper, folding it so the 2 points touch, a wormhole would be a pencil hole punched straight through, creating an instantaneous bridge. This is not science fiction. It is a valid, albeit unstable, solution to Einstein's equations of gravity. The entrance would act like a black hole, drawing you in, while the exit would behave like a white hole, spewing you out into a different time or a distant corner of the cosmos. The problem is one of stability. According to our current understanding, such a bridge would collapse into a singularity in an instant, crushed by its own gravity before even a single particle of light could traverse it. To hold a wormhole open, you would need a form of exotic matter with negative energy density, something that exerts negative pressure to prop the throat of the tunnel apart. We do not know if such matter can exist in the required quantities, or if the universe's laws simply forbid such convenient shortcuts. While no astronomical object has been identified as a wormhole, their mathematical elegance keeps them alive in the minds of physicists, a tantalizing ghost in the machinery of relativity, suggesting that the cosmos might be far more connected than it appears. Our final anomaly exists not in the distant cosmos, but within the very nature of reality itself. It is a thought experiment so unsettling it questions whether you, me, and the entire universe around us are nothing more than fleeting cosmic mirages. This is the Boltzmann Brain paradox. The concept begins with a simple law of physics, entropy, which dictates that systems tend toward disorder. A hot cup of coffee cools down, it never spontaneously heats up. This defines our arrow of time, but in a universe that is truly infinite in age and size, even the most wildly improbable events become not just possible but inevitable. Given enough time, random quantum fluctuations in the void could, by sheer chance, assemble a fully formed, self-aware brain, complete with a lifetime of fabricated memories. This brain would pop into existence for a mere moment, believing itself to be a person living in a real world, only to instantly dissolve back into the chaos. The paradox is this: it is astronomically more likely for a single, disembodied brain to fluctuate into existence with false memories of a past, than for the entire, ordered universe we see around us to have evolved naturally over billions of years. The math of probability seems to suggest that you are far more likely to be one of these momentary, solipsistic hallucinations than a real person in a real cosmos. This is not just a philosophical curiosity, it is a direct challenge to our cosmological models. If our universe is eternal and uniform, then Boltzmann brains should overwhelmingly outnumber ordinary, evolved observers like us. The fact that we observe a coherent, structured universe lasting billions of years is powerful evidence against such a bleak and infinite reality. It forces physicists to seek models where the cosmos has a definite beginning and end, or where the vacuum of space is not perfectly stable, creating a universe where complex life can truly evolve, and where our memories and experiences are not just a cruel, random joke played by the laws of probability. The ghost of the Pioneer anomaly never truly left us. For years, the leading explanation seemed elegant and mundane, a quiet culprit of our own making. The spacecraft's radioactive power sources generated heat, and as that heat radiated away from the probes, the photons themselves carried a tiny amount of momentum, acting like a faint, constant breeze pushing back against their trajectory. This thermal recoil force appeared to solve the puzzle, closing the case with a sigh of relief from many in the scientific community. Yet, when researchers applied sophisticated new thermal models to the decades-old data, meticulously mapping every warm bolt and electrical component, a sliver of the mystery stubbornly remained. The improved calculations could account for most of the observed deceleration, but not all of it. A tiny, residual drift persisted, an unexplained whisper in the data that refused to be silenced by our best engineering models. This leftover anomaly is far smaller than the original signal, But in the world of precision physics, even a whisper can be a shout for attention. So what could be causing it? One compelling possibility lies in the environment the probes are now traversing. The Pioneer spacecraft have moved beyond the dominant influence of the Sun and into the realm of interstellar space. Here, they are sailing through the sparse, ionized gas of the local interstellar medium. Could the gentle drag of impacting on these tenuous particles account for the minuscule remaining force? It is a difficult measurement to make, but it suggests that the Pioneers are now acting as probes of a frontier we have barely begun to understand. The more thrilling, though far less certain, explanation is that this residual anomaly is a hint of new physics. Perhaps it is a sign that our understanding of gravity itself requires a subtle tweak on the scale of the solar system, a modification to Einstein's general relativity that only becomes apparent in the weak gravitational fields of deep space. Or maybe it points to an unexpected interaction between the spacecraft and the quantum vacuum, a sea of virtual particles that fills empty space. The enduring lesson of the Pioneer anomaly is that a mystery solved often reveals a deeper, more subtle puzzle beneath. These two robotic envoys, now silent and drifting in the void, continue to send us a message, not with their radios, but with their unwavering path, reminding us that our maps of the cosmos are still dotted with regions marked "Here be dragons." This cosmic spine, this axis of evil, does more than just puzzle astronomers. It strikes at the heart of a principle that has guided science for centuries. We have long believed we hold no special place in the universe, a concept known as the Copernican principle. It states that our position is ordinary, that the cosmos looks roughly the same in every direction from any vantage point. This idea of cosmic humility is the bedrock of modern cosmology, but the axis of evil whispers a heretical thought. What if, on the largest scales, the universe is not the same in every direction? What if this alignment means there is a preferred frame of reference, a cosmic north that gives the universe a subtle but undeniable structure? It suggests our location might not be so ordinary after all, that we could be looking out at a cosmos with a fundamental lopsidedness, a grand architecture we are only just beginning to perceive. To explain such a profound directional preference, physicists have been forced to consider extraordinary revisions to our cosmic history. Perhaps the period of inflation, the universe's explosive growth spurt right after the Big Bang, was not perfectly uniform. It might have been an anisotropic expansion, stretching space more in one direction than in others, imprinting a permanent directional stamp on the fabric of reality. This would be like blowing up a balloon that is slightly stiffer on one side, causing it to expand unevenly and leaving a lasting warp in its shape. An even more mind-bending possibility involves the multiverse. If our universe is just one bubble in a vast, frothing cosmic foam of other universes, each with its own physical laws, then the axis of evil could be a bruise. It might be the gravitational imprint of a collision with another universe, a neighboring bubble that brushed against our own in the distant past, tugging on the primordial plasma and leaving a scar in the sky. While these ideas push the boundaries of theoretical physics, they demonstrate the profound challenge this single anomaly presents. It is a quiet ripple in the oldest light we can see, a ripple that threatens to overturn our most cherished assumptions about the cosmos and our place within it. The mystery of Tabby's star only deepens with time. New eyes have turned toward this unpredictable sun, with powerful instruments like the James Webb Space Telescope and the Los Cumbres Observatory Global Network capturing its every flicker. The data confirms that the star's bizarre dimming events are real and ongoing, plunging by dramatic percentages in chaotic, unpredictable patterns. The most compelling natural explanation to emerge is dust. Detailed analysis of the starlight during these dimming episodes reveals that blue light is blocked slightly less than red light. This is a classic signature of fine dust grains, which scatter blue light more effectively, allowing more red light to pass through. Imagine driving through a fog at sunset where the red light penetrates the haze more easily than the blue. This strongly suggests a vast, uneven cloud of fine dust particles is orbiting the star, perhaps the debris from a shattered moon or a massive planetary collision. Yet, this seemingly solid answer only raises more difficult questions. Where did all this dust come from, and how is it being replenished? A one-time catastrophic event, like a planet smashing apart, would see the dust eventually dissipate or fall into the star. The fact that the dimming continues for years, with new dips appearing all the time, implies an ongoing, active process. Some astronomers point to a family of giant, crumbling exocomets, their icy nuclei releasing enormous plumes of dust as they swing close to the star. Others propose a recent planetary impact that is still raining debris down onto the star, creating a sustained, swirling shroud. Even with the dust hypothesis, the sheer scale of the required material is staggering, enough to block a significant fraction of a sun-like star's light for years on end. This persistent inability for any single natural model to fully explain the entire light curve, from the deep, asymmetric dips to the long-term, century-long dimming seen in historical photographic plates, is what keeps the door open for more speculative ideas. While the alien megastructure hypothesis has retreated from the mainstream, it has not been entirely abandoned. A few researchers argue that an intelligent origin cannot be ruled out when the natural explanations remain so unsatisfactorily incomplete. The true nature of Tabby's star continues to be written in its erratic light, a celestial cipher that challenges our very ability to classify the strange and the new in our universe. The silent spin of galaxies presents a problem so profound that some physicists are willing to rewrite the laws of gravity itself. This radical alternative is called modified Newtonian dynamics, or MND. At its heart, MND proposes a simple but revolutionary idea that our understanding of gravity is incomplete, not our inventory of matter. It suggests that Newton's familiar law, the one that weakens with the square of distance, only holds true in strong gravitational fields like those within our solar system. But in the extreme weak field environments at the outskirts of galaxies, where the tug of gravity is almost imperceptibly faint, a new regime of behavior takes over. Here, gravity strengthens just slightly, providing the extra pull needed to keep outer stars whipping around at high speeds without any need for invisible dark matter. The success of MND in explaining the flat rotation curves of spiral galaxies is striking. For many individual galaxies, it predicts the observed stellar motions with remarkable accuracy, often fitting the data as well as, or sometimes even better than, the dark matter model. It is an elegant solution that removes the need for a mysterious, unknown substance, arguing instead that we have simply misread the force that governs the cosmos. Yet, for all its elegance on the galactic scale, MND faces immense challenges when confronted with the larger universe. Its most significant failure lies in explaining the behavior of giant galaxy clusters. When galaxies collide in these dense clusters, the normal matter, in the form of hot gas, smashes together and slows down, often separating from the unseen mass that guides their path. We can literally see this separation in phenomena like the bullet cluster, where the gravitational lensing map, which shows where the mass is clearly offset from the visible gas. This provides what many consider to be direct, visual evidence for dark matter as a tangible substance that can be separated from normal atoms. MND, in its original form, struggles mightily to account for this observation without adding some form of unseen matter, which would defeat its core premise. Furthermore, while MND excels with isolated galaxies, it has a harder time consistently explaining the diverse rotation curves of all dwarf galaxies, and it does not naturally fit into the larger framework of the Big Bang and cosmic structure formation. The standard dark matter model, for all its own puzzles, provides a robust scaffolding that explains how the vast cosmic web of filaments and voids could have formed. Has no such comprehensive and successful cosmological counterpart. This leaves us at a scientific crossroads, a choice between two deeply unsatisfying options. Do we populate the universe with a mysterious, invisible substance that makes up over 80% of all matter, a substance that refuses to be detected except through its gravity? Or do we alter a fundamental force, a law that has held true for centuries in our own celestial backyard, to explain galactic motions, even if that altered law then fails to explain the cosmos on its largest scales? This is not merely a technical debate, it is a battle for the soul of physics, a reminder that our most trusted maps of reality are still being drawn, and that the cosmos delights in presenting us with contradictions that force us to think deeper. The battle over the universe's expansion rate has sparked a race to find a solution, pushing cosmologists to explore radical new ideas. One of the most compelling proposals involves dark energy not being a constant force, but one that changed over time. The idea of early dark energy suggests that a new, temporary form of this repulsive energy existed in the universe's first few 100,000 years. This extra push would have subtly altered how the primordial plasma sloshed and rippled, changing the sound waves imprinted on the cosmic microwave background. This tiny adjustment to the early universe's physics could allow the CMB to predict a faster modern expansion rate, finally aligning it with what we see in our local neighborhood. It is like discovering that a runner had a strong tailwind for the first part of a race, which would change our expectations of their finishing time. Another fascinating possibility is that dark matter, the universe's invisible scaffolding, is not completely passive. In interacting dark matter scenarios, this mysterious substance might decay or interact with dark energy or even with itself, releasing energy that subtly boosts the expansion rate over cosmic history. Imagine a slow-burning fuel mixed into the cosmic engine, providing a little extra oomph that we did not account for in our original models. Of course, many scientists still scrutinize the measurements themselves. Could there be a hidden cumulative error in how we use Cepheid variable stars as cosmic yardsticks? Perhaps these pulsating stars are not the perfect standard candles we believe them to be, or maybe interstellar dust is dimming their light in ways we have not fully corrected. This is where our newest window on the cosmos comes in. The James Webb Space Telescope, with its infrared eyes, is now piercing through that cosmic dust, observing Cepheids with unparalleled clarity at the very hearts of distant galaxies. It is performing a direct, clean measurement, cross-checking the cosmic distance ladder rung by rung to see if a subtle flaw in our vision is the source of all this tension. Each proposed solution, from evolving dark energy to flawed measurements, carries profound implications. If early dark energy is real, it means the cosmos underwent previously unknown evolutionary phases. If dark matter interacts, it is far more complex than a simple ghost, and if it is a measurement error, it would be a humbling lesson in the difficulty of cosmic cartography. The resolution to the Hubble tension will not just give us a number, it will force us to choose a new path for the future of cosmology, revealing which of our fundamental assumptions about the universe was wrong all along. The Boltzmann Brain paradox forces us to confront the ultimate fate of our accelerating cosmos. This unsettling thought experiment is inextricably linked to one of the greatest embarrassments in theoretical physics, the cosmological constant problem. Our best theories of the quantum vacuum predict that empty space should be seething with a tremendous energy, a vacuum density so powerful it should have ripped the universe apart in its first moments. Yet, we observe a universe that has expanded at a far more leisurely pace for billions of years. The measured value of dark energy is a staggering 120 orders of magnitude smaller than the theoretical prediction. It is the worst mismatch between theory and observation in the entire history of science. If the vacuum energy were even slightly larger, galaxies and life could never have formed. This incredible fine-tuning seems like a cosmic miracle, a number set with impossible precision to allow for our existence. The Boltzmann Brain offers a terrifying perspective on this miracle. In an eternal universe dominated by a small, positive cosmological constant, the vacuum of space will eventually become the dominant environment. Stars will burn out, black holes will evaporate, and all matter will decay into a thin, cold haze of particles. In this final, eternal state, the most common form of consciousness would not be one that evolved on a planet, but a lone brain that spontaneously fluctuated into existence from the quantum foam. The fact that we do not appear to be such brains is powerful evidence that our universe is not eternal in this way, that it has a finite future and perhaps a definite beginning. This leads directly to the measure problem in cosmology. How do we count observers in a vast, possibly infinite multiverse? If every possible universe exists, then for every one like ours with a history of stars and galaxies, there could be an infinite number of empty universes producing Boltzmann brains. Our experience of a structured cosmos would then be an infinitesimal statistical fluke. The paradox forces physicists to seek models where the vacuum is not perfectly stable, where our universe can eventually decay or transition, cutting short the era where Boltzmann brains would dominate. It suggests that our very existence as coherent observers is a profound clue, a cosmic datum pointing toward a deeper structure to reality, one where the constants of nature are not random, but perhaps selected for their ability to create lasting worlds where minds can truly grow and belong. From ghostly spacecraft decelerations to the silent pull of dark matter, these 25 cosmic glitches form a mosaic of profound uncertainty. We have navigated the strange tugs on our probes, witnessed entire galaxies flowing toward an unseen horror, and grappled with stars that wink out of existence for reasons we cannot explain. We have listened for signals from the void and found only a fleeting, tantalizing whisper. The very laws of physics, from the quantum realm's spooky connections to the stubborn conflict between relativity and quantum mechanics, reveal themselves to be incomplete descriptions of a far stranger reality. Each anomaly, whether a missing satellite galaxy or a universe expanding at the wrong speed, is a crack in the foundation of our knowledge. Collectively, they are more than just puzzles, they are a chorus of cosmic dissent, challenging the very definitions of space, time, and existence. They force us to admit that our most trusted maps of reality are still provisional, dotted with vast regions marked unknown, so we turn this final question over to you. After this journey through the universe's greatest mysteries, which single anomaly keeps you awake at night? Is it the possibility that our entire cosmos has a preferred direction, an axis of evil written into its first light? Or does the idea of a universe fine-tuned for life, yet seemingly filled with Boltzmann brains, shake your sense of what is real? Share your thoughts in the comments below and let us know which cosmic secret you find most compelling. If unraveling the fabric of reality captivates you, subscribe for more journeys to the edge of our understanding, where the next great discovery is always waiting in the dark.